Let's take a look at example 18.2 for the differential amplifier. A diff amp has a differential voltage gain of 2500 and a CMRR of 30,000. In the first part, a single-ended input signal of 5 microvolts RMS is applied. At the same time, a 100 millivolt 60 hertz common mode interference signal appears on both inputs as a result of radiated pickup from the AC power system. In the second part, we're going to look at the differential input signals of 500 microvolts RMS each applied to the inputs. The common mode interference is the same in both parts here. So the first part here, we're going to determine the common mode gain. We're given the differential gain as 2500 and CMRR of 30,000. So from that, we can calculate then the gain from the common mode. So CMRR is equal to the gain differential divided by the gain of the common mode. Therefore, solving for the common mode by moving the terms around, we have the gain of the differential and CMRR 2500 divided by 30,000 gives us a gain CM of 83 hundredths. So that's our ACM. In the second part, they just want us to express the CMRR in decibels. So CMRR in dB is equal to 20 log of the value of CMRR that was given. So CMRR decibels is equal to 20 log times 30,000, which gives us 20 times 4.47 and a CMRR dB of 89.5 decibels. Next, we want to determine the RMS output signal. The differential input signal, VN differential, is the difference between the voltage on input 1 and that on input 2. Since input 2 is grounded, the voltage is 0. So given VN1 500 microvolts, VN2 0, therefore VN differential is equal to the difference in those two inputs. So VN1 minus VN2 is 500 microvolts minus 0, which gives us then 500 microvolts, just whatever's on pin number 1. The output voltage in this case is taken at output 1 over here. So output 1 is the gain differential times the voltage in differential. 2500 times 500 microvolts gives us 1.25 volts RMS. In C, we want to determine the RMS output signal. So this time we're going to apply the 500 microvolts to both inputs. So again, we take the difference in the two, VN1 minus VN2. This time, since we have one on the inverting and one on the non-inverting inputs, we end up with a sum of 500 and 500 microvolts, which gives us 1000 microvolts, which we simplify to 1 millivolt. The output voltage then, Vout1, then is the gain of the differential times the voltage in differential. So we just solved for the voltage in differential, 1 millivolt. We're going to multiply that times the 2500 that was given to us, and we get 2.5 volts RMS. So this shows that a differential input, two opposite polarity signals, results in a gain that is double that for a single-ended input. Finally, in D, the last part, we want to determine what's going on here, determine the RMS interference voltage on the output. So we're going to impress some noise on the output and see what happens here. So the common mode input is 100 millivolts RMS. The common mode gain then we solved for 83 hundredths. The interference voltage then on the output, therefore, is ACM, the common mode gain, is equal to V out CM by VN CM. So if we turn things around here, we can solve for V out. So the ACM times 100 millivolts, 83 hundredths times 100 millivolts gives us a voltage out then of 8.3 millivolts. This becomes the interference voltage on the output. So the differential amplifier.